Number 52, Math 110 final review. Write the following as the sum or difference of logarithms. So we have this big log expression. We've got log of this. Of course, there's no subscript on the log, so that means we're dealing with base 10. There's always a base for the logarithm, but the properties of logs don't matter what base it is. So it could be base 10, it could be ln, base e, or just a generic base b. But this expression has chosen to write it as just log base 10. And we've got this big fraction. The object is to split it up and write it into as what's called a linear combination of several logs, where you're just taking multiples of logs of single variables and adding or subtracting them. So first of all, there's a property of logs that says if you have log of a quotient, that's equal to the difference of the log of the numerator and the log of the denominator. So log of a fraction is log of the top minus log of the bottom. And these properties are all related to properties of exponents, but you just have to memorize them. Then when you have log of a product, x cubed times the square root of y, that can be split up into log of the first factor plus log of the second factor. All right, so product of a log of a product, log of a product can be split up into a sum of logs. Let me just write this one down. And then the other property is when you have log of something to a power. That power can come in front as a coefficient. So this is log of x cubed. That turns out to be the same thing as 3 times log of x. This is log of the square root of y, and here's where you want to remember that the square root is the 1/2 power. So let me leave some space here. So that 1/2 power can be brought out in front of that logarithm as a coefficient. So we have 3 log of x plus 1/2 log of y. And then finally minus that power on the z, that 4 can come out in front as a coefficient of that logarithm. And this then is your final answer for breaking that all the way down into logs of just a single variable. Sum or difference of logs. Number 53 is going the other way around. It says write the following as a single logarithm. So notice here we have a string, a linear combination of logarithms, and we want to go back to writing it as log of a single expression. So let me write that down. Number 53, 1/3 log base 4 of x. So now we have a base of 4. But it doesn't matter. As long as they're all the same base, which they are, then we can use these properties. And up here it was all base 10. Down here it's all base 4. Base 4 we have to write as a subscript. Base 10 is understood. All right, so first of all, this coefficient goes up as a power. So 1/3 times the log base 4 of x is the same thing as log base 4 of x to the 1/3 power. And then minus this 2 can go up as a power of the y, log base 4 of y squared. And finally this 6 can go up as a power of z, so we have log base 4 of z to the 4th. All right, now I'm going to do 2 things at once here. This is difference of logs, so that can be combined into a single log of the quotient. So we're going to have x to the 3rd over y squared, and also I'm going to change that 1/3 power to a cube root. 1/3 power is the same thing as a cube root. Cube root of x over y squared is combining those two into a single log, and then plus log base 4 of z to the 4th, we want to then change that to a log of the product. And this is over 1, so that z to the 4th joins the cube root of x in the numerator. I'll go ahead and write that in front of the radical so it doesn't get confused as in the radical. So we've got z to the 4th, cube root of x, all over y squared. And there's the answer for combining that all into a single logarithm. All right, 54. For the function y equals 2 to the x plus 1 minus 3, determine the domain, range, and equation of asymptote, and graph the function. All right, so here's where you want to remember that an exponential function has domain all real numbers, because you can put anything into the power that you want to, and it's still defined. You can still get a number. And so if you add 1 first before you take the exponential and subtract 3 after, that's still not going to affect any restrictions. So the domain is still going to be all real numbers, minus infinity to infinity. Now the range is restricted because when you have an exponential, it can only be positive. So 2 to any power is going to be always greater than 0. So this has a shift down 3. So that just means it's always greater than negative 3. So the range is going to be negative 3 to infinity, not including negative 3. All right, then from there, it's helpful if you remember that the doubling function 2 to the x is just a general exponential growth that has y-intercept at 1, because 2 to the 0 is 1, and horizontal asymptote at the x-axis, again, because it can't be negative. So it does something like this. So then if you shift it to the left 1, remember a plus 1 with the x inside the function is a left shift. So that'll move that y-intercept to the left 1. And then down 3 will not only move that point down 3, but the asymptote down 3. So that y-intercept gets moved to the left 1 and down 3, right there. This horizontal asymptote gets moved down 3 to negative 3. And otherwise, it's got that same exponential growth. There are x and y intercepts here that you could find. The x-intercept, remember, is when you set the function equal to 0, plugging in 0 for y, you would get 2 to the x plus 1 minus 3 equals 0. So 2 to the x plus 1 equals 3. To solve that equation, you've got to take the log of both sides. Log of 2 to the x plus 1 equals log of 3. And then you can use that property of logs that says you can bring that x plus 1 out in front. X plus 1 times the log of 2 equals the log of 3. So x plus 1 equals the log of 3 divided by log of 2, dividing both sides by log of 2. And finally subtract 1 from both sides to get x equals log of 3 over log of 2 minus 1, which you'd have to type into your calculator to get an approximation for. Let's see. Log of 3, gotta close that up, divided by log of 2, and those are just numbers, kind of like square root of 3 and square root of 2, just irrational numbers, minus 1, approximately 0.58. So that's the x-intercept. All right, so I didn't draw it quite steep enough, right? If the x-intercept is 0.5 something, that's a little steeper. then I drew it. And then the y-intercept, let's see if I got that. The y-intercept is where you plug in 0 for x. So we should be able to calculate that. 2 to the 0 plus 1 minus 3 is 2 minus 3, or negative 1. It looks like I got that one pretty close. There's the y-intercept. So you can get those points at least approximately by setting it equal to 0 and solving for x to get the x-intercept, and plugging in 0 for x and calculating y to get the y-intercept. Otherwise, that's the graph. And of course, the other way to look at it, or at least check it, is to type this into your calculator as y equals. We've got 2 to the quantity x plus 1 power minus 3. Here's a standard window, and you can see, sure enough, it levels off right there at about negative 3, comes through the y-axis. In fact, after you graph a function in the standard mode, zoom standard, minus 10 to 10, if you hit trace, first thing it lands on is the y-intercept. So that's always nice if you want to graph something and then just hit trace. You can see the y-intercept right off the bat. Of course, the x-intercept you could find with second calc 0 by giving it a left bound and a right bound and hitting enter for a guess. And there it gives you approximation. Not a real nice number, that log of 3 over log of 2 minus 1, but 0.58, 0.5849. In fact, if we quit out of there, you can probably see that's the same approximation either way. So that gives you your graph. So your domain, all real numbers, because it extends infinitely to the left, infinitely to the right. Your range, minus 3 to infinity, because it's bounded below by negative 3, not including that value, and it's not bounded above.